Chapter 14 is about compression members that fail before they reach the yield strength of the material. They fail because of their shape. We think of columns as parts of buildings, but we also see them in machine parts. A connecting rod in an internal combustion engine is a column because it supports an axial load in compression. We can classify columns as short, intermediate, or slender. A short column made of a ductile material will squish outwards when loaded in compression, while a short column made of a brittle material will crack. Short columns start to fail when they reach the yield strength of the material. An intermediate length column will form a kink as it buckles. This happens below the yield strength of the material. You can try this out with a short length of solder, which is typically made of a soft alloy containing tin. A slender column will bow when it's overloaded. You can try this by cutting out the bottom part of a steel coat hanger and pressing on its ends. The math for column buckling was developed by Leonhard Euler, the mathematician who invented the e to the x button on your calculator. He determined that the load required to get a slender column to buckle is equal to pi times Young's modulus times the moment of inertia divided by the length squared. We call this the critical load. When you calculate the critical load, make sure you use the smaller value of I, because the column will buckle in the weaker direction. In this example, we have a rectangular cross-section of 0.1 inches by 0.2 inches. The weak direction is I sub y, so we plug I sub y into the Euler critical load equation, and we find that it will buckle under a load of 3.8 pounds. If this column were loaded in tension instead of compression, then the tensile load it can carry would be equal to yield strength times cross-sectional area. Let's say the yield strength is 40 ksi. Multiply 40 ksi times 0.1 inches times 0.2 inches, and it can support a tensile load of 800 pounds. This is more than 200 times greater than the buckling load. You know of other materials that can support a high tensile load but very little compressive load. A good example is string. Cast your mind way back to Chapter 6, where we calculated the radius of gyration of a cross-sectional area. It's equal to the square root of I over A. Divide the Euler critical load by the cross-sectional area of a column, and you have the critical stress. This is the stress in the column when buckling starts, and it's less than the yield strength of the material. Substitute the formula for critical load, and we can find the critical stress is pi squared times E divided by L over R sub G squared. The ratio of L over R sub G is called the slenderness ratio. The scale at the bottom of the screen shows slenderness ratios for a range of objects. A piece of chalk straight out of the box is not as slender as a brand new wooden pencil. Utility poles have a range of values because although their lengths are pretty standard, their diameters are not. Columns are supported in different ways. If the ends of the column are free to rotate, like the ends of a connecting rod in an engine, then we say the column is pinned. The purple line shows that a pinned column develops a curved bow along its entire length. If the ends are fixed, like the wall end of a cantilever beam, then the ends cannot rotate. This is called a fixed column. The column is perpendicular to the connection points. Then, at some distance from the connections, it starts to bow. The bow is not as much as a pinned column, so we say that the effective length of the bow is shorter. In fact, it's half of what you get with a pinned column. If we fix one end and pin the other, then we have a fixed and pinned column. Now the effective length is 70% of the column length. We can assign a value to the portion of bow. It's called the K value. K is the effective length divided by the total length of the column. A flagpole has a fixed connection at one end, but no connection at the other end. The free end can move laterally as well as rotate. We end up with half of the bow shape of a pinned column, so we can imagine a mirror image of the bow below ground and say that the effective length is twice the column length, so K equals 2. In order to include the end supports into our critical load and critical stress equations, we multiply length times K. This is all fine in theory, but in the real world, other variables can reduce the critical load and critical stress. For example, the load may not be perfectly aligned with the axis of the column, or the design load might be exceeded unexpectedly, or there may be manufacturing defects in the column material, or there may be damage to the surface of the column, such as scratches or nicks. Therefore, we should include a factor of safety into the equations, and we do that by putting it in the denominator. The factor of safety covers what we don't know about the material and loading conditions. Some engineers call it a factor of ignorance to cover what we don't know. Chapter 14 includes two special cases of columns: structural steel wide flange beams and steel machine parts. There are formulas for other special cases, such as timber and aluminum, but we won't cover these special cases in the book. AISC is the American Institute of Steel Construction. AISC has a 4-step process for designing safe columns using W-beams. First, calculate two numbers using column dimensions and materials properties. Second, calculate the critical stress in the column. Don't use a factor of safety because that's incorporated later in the AISC formulas. Third, check KL over R sub G. If it's greater than 200, then AISC has found that the column is too slender for safe use. This comes from practical experience. If KL over R sub G is greater than 4.71 times the square root of Young's modulus over yield strength, then the allowable load is a constant times the critical stress times the cross-sectional area. The constant includes a factor of safety that works for steel construction. On the other hand, if KL over R sub G is less than the magic number, then the allowable load formula is a little more complicated. The factor of safety is in the denominator. It's the same factor of safety we used in steel beam problems. Finally, you can find the actual stress in the column by dividing the allowable load by the cross-sectional area of the column. Let's see how this works in an actual column. Here's a fixed column, so K equals 0.5. You can find R sub G X and R sub G Y in Appendix D. Use the smaller value because the column will fail in the weak direction first. We calculate KL over R sub G, and 4.71 times the square root of E over yield strength. The results are unitless. Now we calculate the critical stress, and it's 26.8 KSI. KL over R sub G is less than 200, so it is safe to use. Since KL over R sub G is less than 4.71 times the square root of E over yield strength, we use the second of the two allowable load formulas. Plug in the values, and we get an allowable load of 258 kips. The tricky part of the calculation is 0.658 raised to a weird exponent. The last step is to find the actual stress in the column. It's 14.6 KSI, which is much lower than the yield strength of the column. Why do we care about stress? Because we can attach a strain gauge to the column before it's loaded, and then monitor conditions after it's loaded. A strain gauge measures strain, and since we know that stress equals strain times Young's modulus, we can use the readings from a strain gauge to determine the actual stress in the column. As long as the actual stress is below 14.6 KSI, we know the column is safe. The other special case discussed in Chapter 14 is steel machine parts. We calculate KL over R sub G, then compare it with the square root of 2 pi squared times Young's modulus divided by yield strength. If the column is slender, the math is pretty simple. We're back to the Euler equation for allowable stress. Allowable load is stress times area. On the other hand, if the column is intermediate, then the formula is more complex. This formula was developed by J.B. Johnson around the year 1900. Let's look at an example. Here's a 2 centimeter diameter round rod made of 4140 steel. It's 40 centimeters long. We'll use a factor of safety of 2. KL over R sub G is 80, and the square root of 2 pi squared times Young's modulus over yield strength is 98. Therefore, the column is intermediate, and we can use the J.B. Johnson formula. Allowable stress is 141 megapascals, which is about a third of the yield strength of the steel. Allowable load is 44 kilonewtons. The book includes 5 fully worked out examples of column problems. One very common mistake is to mix up the formulas between W-beams and steel machine parts. So make sure you're solving the right kind of problem.